Oh, good, great, thank you. turn it on. Okay, so in an integrated circuit, what you can do is you can apply a drain to source voltage at the terminals, right, the tungsten contacts. And in response, if the gate is biased above the threshold voltage, then you can get current to flow. Okay, so this is ID sat. Okay, but this ID sat, let's say in the saturation regime, flows through the source and drain regions as well, right? Okay, so there's going to be, so the source and drain regions will have to have some voltage dropped across them, like this. Okay, so the actual voltage that appears across the channel, across the inversion layer in your device is going to be VD sat, and on this slide we call it VD sat not. Okay, actually it's not on this slide, probably. Okay, so which VDS which VDS actually determines the current flowing? I'll just call this VDS not. It's actually VDS not that determines the current flowing through the transistor, right? Okay, so what this means is that you're applying some drain to source voltage, but you're not really going to get as much current as you expected because you're losing some of that applied voltage across the source and drain, resistive source and drain regions. Okay? And so basically just qualitatively, assuming that this is a short channel MOSFET. Okay, so why is this more of a problem for short channel MOSFETs than for long channel MOSFETs? That's right. So as Will said, when the channel length gets really short, then when the transistor turns on, the resistance is relatively small. Okay, for a long channel device, when you turn it on, because it's longer, it has a larger on-state resistance. So the source and drain regions, even if they have some resistance, is kind of small compared to the channel resistance. So yeah, basically you think of it as a voltage divider, right? There's some, in the on-state, there's some channel inversion layer resistance, and then there's some source and drain resistance, okay? And if this is really large, then most of the pretty much all the voltage will be dropped across it. But when you scale down the size of the transistor, the length of the channel, then our channel gets smaller and smaller because you can conduct more and more current, right? You have higher and higher drive current when you scale the transistor down. So the parasitic resistance really becomes an issue when you're trying to scale to very, very short channel lengths. Okay? All right. Good. So in this slide, we assume, let's say it's for a short channel MOSFET. So assuming velocity of saturation so that the current actually is only proportional, ideally, to VGS minus VT rather than the quantity squared. It's relatively easy to derive this equation that just tells you what the real current flow is due to parasitic source and drain resistance. So RS is just the series source and drain resistance. Okay, so we add them together. Okay. So basically, there's going to be some total voltage drop across the source and drain resistances, and depending on how large that is compared to the VGS minus VT, this is kind of representing the VD sat. Right. So, in the saturation voltage depends. Saturation current depends on the saturation voltage, which depends on is directly proportional to VGS minus VT. So depending on how large this voltage drop is across the series resistors, the resistances, compared to the voltage dropped across the actual channel, that's going to tell you how much you degrade the on current by. Okay, so easily you can degrade the current by more than 10% in a modern submicron MOSFET or deep submicron MOSFET. And in order to reach saturation electric field, you need to apply more voltage to the terminals because you're losing some of that voltage across the series resistance. So basically the current, so if you look at current versus output voltage, ideally it might look something like this. With series resistance, okay, what I'm saying is you have to apply a larger voltage before you see the saturation, but you're also going to saturate at, like more than 10%. lower voltage. So just look a little bit more smeared out, and you won't reach as high of a saturation current. Okay. Any questions qualitatively about series resistance? Yes.
So the RS
Okay. So your question is this RS? Okay. So the RS in this equation is.
different from,
Oh yeah. Okay.
or
Hold on.
is RS equivalent to that RS plus
Yeah, that's a good question. Let me think. Actually, it's probably the same. Okay, so I forgot to mention. So you have series resistance in the source and drain. Which one is actually going to degrade the current more? The source, right? Because this voltage dropped across the source. Let's call this V source. I don't know. That will also effectively reduce the gate to source voltage that is applied to the intrinsic transistor. So RS, the resistance of the source, actually will directly impact the gate, the applied gate to source voltage. I mean, the real gate to source voltage. So that's a good point. So this really is the resistance of the source, okay? And then the resistance of the drain actually serves to further reduce the current, but also contributes to making the saturation drain to source voltage higher. Yeah. Yeah, thanks. Okay. Now, on this slide, on the previous slide, I also showed. So here's the tungsten, let's say the typical tungsten, say, contact material. And here's the silicide. So typical silicide today is nickel silicide. Okay. So you can say, well, okay. And this is a practical issue. We can actually just make the silicide thicker, right? We can react more metal with semiconductor to make this silicide thicker, to reduce the parasitic resistance, right? We could. All right. So it turns out that if you do that, you start to see significant leakage current. Actually, I'll just say it's from the drain p-n junction. Okay, so do you remember what happens in a p-n junction if you bring the metal contact too close to the metallurgical junction? What do we call that when the quasi-neutral region is really short? Short base? A short base diode? Okay, so what happens with a short base diode? And what happens to the current? The leakage, the reverse leakage current, right? Because these p-n junctions, the drain and the source and drain p-n junctions, those are supposed to be at the most, they're supposed to be reverse biased or zero biased. Okay, so let's look at the drain junction. When the transistor is on, there'll be some reverse bias. So what happens to reverse bias leakage current when the p-n junction, one side of the p-n junction is too short? I don't remember. Okay. So what happens to the gradient of minority carriers in the? It gets steeper, right? Right. The concentration profile of excess minority carriers in a short diode region, it gets steeper if you make the diode shorter and shorter. So that means the diffusion current is increasing, right? Yeah. So basically, that's one reason why we have to be very careful, especially over here, in this region here. You can't overly silicide, or you can't aggressively scale down the depth of that p-n junction, or you can't overly silicide the junction. So actually, in the most advanced, maybe only the most advanced technologies today, they're starting to eliminate the silicide, because there's like the junctions are getting so shallow, there is no space to form a silicide. Okay. Okay, so before I talk about modern transistor structures, let's just summarize that in a MOSFET, for digital logic applications, we care about two things. We care that when the gate voltage is 0, that there's very small leakage current. Okay, so we don't really want to have current flowing between the source and drain regions when the gate to source voltage is 0. And in the off state, the current, that leakage current that flows is due to carrier diffusion, right, over the source potential barrier. So, okay. Now you want the gate to control the channel potential very well to get steep subthreshold swing. So ideally, there might not be room to draw in here. So this normal, what we call transfer characteristics, the current on a log scale versus the gate to source voltage. Well, okay, I'm not drawing it perfectly well here. Let's try again. So it's below threshold, it looks like a straight line, and above threshold, it curves over because this is a log scale. Okay, so the subthreshold swing, that determines the off-state leakage for a given threshold voltage. Okay, so if we want to have a low off-state leakage current flowing, then we want a steeper subthreshold swing. Okay, so that tells us how we should dope the channel. So generally, you'd like to dope to make the subthreshold swing steep. Okay, like close to 60 millivolts per decade, which is the ideal case, the best case. Do we want to dope the channel heavily or lightly, just generally? Subthreshold swing, 1 plus C depletion over C aux times 60 millivolts per decade. That's the subthreshold swing at room temperature. Yeah, we want to dope it lightly, right, to have subthreshold swing steep, to have low off-state current. But what happens to drain-induced barrier lowering if you make the channel more lightly doped? You get more drain-induced barrier lowering because the width of the depletion region, right, the width of this p-n junction depletion region gets wider, right, if you dope the channel or the body region more lightly. So you get drain-induced. So the drain voltage will start to influence the source potential barrier more so if you lightly dope the channel. See, so this is why in your design project you're going to see this trade-off. If you improve one aspect of your device, you might degrade some other aspect. Okay. So that's one requirement for a digital logic transistor: low off-state current, and it's important to have low off-state current when you have high drain to source voltage. Okay, so that's important to understand the application, right? Okay, now in the on state, so you'd like the circuit to operate quickly, so you'd like to have as high drive current as possible. Okay, when a transistor is turned on, you have the very, very small potential barrier for carriers to diffuse from the source into the channel. So what limits current flow is not the diffusion of carriers into the channel. It's the rate at which carriers drift across the channel from the source to drain. Okay? So these are basic things you should remember. So in the off state, current is limited by diffusion. In the on state, current is limited by the drift velocity. Now, if you want to have lots of current, then how would you dope the channel? Heavily or lightly? Lightly, right? So first of all, the mobility should be higher because there's fewer ionized dopants around. But the threshold voltage will be lower, so you have more current. But then short channel effects get worse. Okay. So you just have to keep in mind that there are some non-ideal things that can limit on-state resistance, and you want to be able to operate with reasonably large VDS without having current flow out of control of the gate. Okay, so that's punch through. So punch through is not good simply because the gate really can't control that current very well. It actually occurs beneath the surface of the silicon. Okay, so are there any questions just generally about these qualitative phenomenon that occur in modern day transistors? No? Okay, so let's talk about how the transistors are fabricated. And then I'll show you cross sections of actual transistors used in integrated circuit products today. All right, so in this CMOS technology, you have both NMOS and PMOS transistors, of course, that are always fabricated in complementary, most of the time in complementary pairs. Okay, so we start with a wafer. Typically, it's actually P-type. So these are cross-sectional views of a silicon wafer, and just looking at the near surface region. So in order to make NMOS devices, we want to have a P-type substrate, right? P-type body region. And for PMOS, P-channel devices, we want to have an N-type body, right? So we need, if we want to make N-channel and P-channel transistors sort of side by side on the surface of the silicon, we need to have surface regions that are P-type next to surface regions that are N-type. And so what we do is we selectively introduce N-type dopants into the near surface region of the wafer. And so these are, depending on the company you work for, generally we call them wells. Okay, so this is an N well located within a P-type substrate. Now P-type substrates are typically like greater than 1 ohm centimeter. I mean, they're relatively lightly doped. Okay, they're pretty pure. And so in a modern CMOS technology, you don't want such a lightly doped body region. And so you would also want to form a more heavily doped P-type well in your substrate. So you basically have to have two implant steps, masked implant steps to selectively form the N-well regions and the P-well regions for the PMOS devices and the NMOS devices respectively. Okay. Okay, so these comments here are just, okay, let's review. In a CMOS technology, what would be the typical bias of the P-type region, P substrate? It's, okay, it's either 0 or the supply voltage. Okay, which one? For the P-type substrate, yeah, you would ground it. And here, the N-well, you'd maybe have a little contact, some metal, and that would be biased at VDD. Okay, so N-type regions are usually biased at the highest possible voltage, so you'll never get a forward bias p-n junction to cause current to flow into and out of that well. Okay, so you have a reverse bias p-n junction here, right? P substrate N well. And this comment here is just saying, all right, if this P-type substrate is very lightly doped, what does that say about the depletion width on the P side? Very big. So basically, that little bullet there is just referring to the fact that, okay, we want this P substrate not to be all the way, fully depleted, so that you can actually suddenly have current flowing between the N well and this back, substrate contact. Okay, so that's what we call punch through. All right. Yes, Ali. How big are those wells? Okay, so the wells, depending on the generation of technology, is on the order of maybe a micron deep. And then the lateral dimensions just depends on how many transistors you want to hold within the well. So usually in a, let me just, CMOS? In the CMOS, I talk about CMOS circuits. Is it here? Okay, so remember we were talking about simple NAND gate and NOR gate. So usually the transistors, the pull-up transistors are all in one well, and pull-down transistor networks all in another well. Okay, so usually the wells hold multiple transistors. Yeah, because there's really no reason to, well, the NMOS and PMOS transistors are usually laid out side by side, so there's no reason to form separate wells for them. Okay, I mean, separate wells for the same, for PMOS transistors. You just want a separate well for PMOS versus NMOS, but not, PMOS versus PMOS. And they're all biased at ground, or I mean, so this N well here is biased at VDD for many transistors, and then the P well or the P-type substrate is grounded for many transistors. Okay, so the question is, why don't we put a space between the N well and P well? What would the purpose of the space be? So you don't have a p-n junction. Okay, but you always have a p-n junction because okay, so let's say if we space this p well over here instead, right? The substrate is going to be either p or n type, so you're always going to have a p-n junction like that. You can't avoid it, unfortunately. Yes, Haley. Okay. Is there a reason why we start with either P or N rather than a intrinsic substrate? It's probably just it's to get reproducible results. So intrinsic means that you have absolutely no impurities. Okay. All right. So P substrate, let's say greater than 10 ohm centimeter. The dopant concentration is. Let's see. Okay, wait. It's like 10 to the 15, 10 to the 14 per centimeter cubed. So how many parts per million impurities is that? Like if you have 10 to the 14 per centimeter cubed. That's like, I mean, it's like 10, approaching parts per billion. And so in practice, it's not easy to get such high purity material. I mean, it is. It's not easy. In other words, it's more expensive, right? So it's all a matter of cost, right? So if you want a reasonable cost substrate, then it's just easier to make it, P-type or N-type, 10 to the 14, 10 to the 15 per centimeter cubed. You can easily, buy that. And then it doesn't really degrade the device performance so much. Okay, so remember, in the mobility versus doping plot, you really only see the mobility start to affect the mobility. Sorry, the doping start to affect the mobility at what level of doping? Do you remember where that plot sort of falls off? For electrons and for holes, how the mobility. So this is mobility versus doping so this Na plus Nd on a log scale. Do you remember where this happens? It's around 10 to the 14, 10 to the 15, yeah. So as long as the substrate is doped like a little bit, it's not really going to degrade the device performance too much. Okay, all right. Okay, so the question is the N well and P well doping, are they pretty uniform across the substrate or vertically? Yes, so locally it might tune the threshold voltage by BT implants, but usually the well doping is the same most of the time across the entire chip for NMOS, for all NMOS devices and for all PMOS devices. That's pretty typical, yeah. The well doping profile is not perfectly uniform vertically, because it's formed by ion implantation, so it's usually more heavily doped up here, and then at the metallurgical junction, then it's more lightly doped. Okay, so let's look at the fabrication process. Oh, okay, so that was just a general concept of forming separate wells to allow you to form PMOS and NMOS devices side by side at the surface of the wafer. Okay, so we start with a substrate, and then we actually go through various process steps to form the NMOS and PMOS transistors. Now, one thing we can do to allow the transistors to be spaced more closely together, the NMOS and PMOS devices to be spaced more closely together, is to actually dig a trench in the surface of the silicon and to fill it with silicon dioxide. Okay, let's explain why that's the case. Okay, so if you have wells side by side like this, let's see. Well, there's going to be a depletion region, right? And so basically, you can't fabricate transistors with those depletion regions there. So you have to basically space the transistors farther apart to account for the depletion region. But if you actually just, rather than having silicon in between the transistors, you can just have silicon dioxide. You can actually make the silicon dioxide narrower, and you can fit transistors, pack transistors closer together. Right? So you can fit more transistors per unit area, get more functionality, lower cost per function, and so on. Okay, so this is what we call shallow trench isolation oxide. And that typically, that depth is on the order of, let's say, 0.2 microns, tenths of microns deep. So as I mentioned, the wells are usually a little bit deeper. But what happens is then we form, because we're forming the transistors only in the top less than 1 micron of the surface. So basically, we care about isolation up here the most. OK, so then we form the shallow trench isolation. This process involves high temperature processing or high temperature annealing to form a high quality interface between the silicon dioxide and the silicon. Okay, so you don't have carriers, interface trap states, interface traps. So to form a high quality interface between the silicon dioxide and the silicon, you have to subject it to high temperature processing. And you don't want to have dopants in the silicon diffusing all over the place when that happens. So that's why you generally form the wells after you form the shallow trench isolation regions. Okay? And then you can actually dope the surfaces in different regions of the chip to tune the threshold voltage as you want it. Okay? Then you form a gate dielectric layer, the oxide layer, that separates the gate from the silicon channel region. And then you form the gate electrodes. So this is all, you deposit a film, and then you pattern it using lithography and etch, which you can learn about in a class like EE143. So the key is you form the gates first, and then the gates naturally act as a mask. So when you implant your ions, so you can implant, this is NMOS on the left, right? So you can implant like arsenic here on the left side, and you can implant in a separate step boron ions, actually. It's a uniform process. It's like a blanket implant, okay? But wherever there's a gate, the gate electrodes block the implant from reaching the silicon. So this way you can form the source and drain regions in a self-aligned manner. Okay, so the source and drain regions are the source and drain dopants are introduced in regions that are well aligned to the edges of the gate electrodes. Yes, Pera. Okay, so the question is, how do the implanted dopants affect the gate material? So remember, for an NMOS device, what typically do we dope? If we have a polycrystalline silicon gate material, what is typically the dopant type? Yes, so for NMOS, we have an N+ gate. For PMOS, we have a P+ gate. So actually, the implants also dope the gate, N-type or P-type. Okay, but they also prevent the dopants from getting into the silicon, so you can form a self-aligned channel. Oh, okay, so if the gate material is a metal, well, if you implant dopants into a metal, it's still metallic, so it could potentially affect the work function of the gate, but yeah, I don't think people have actually studied that too much. But usually the effective work function of the gate, of the metallic gate, is not affected too much by implanting these kind of dopants. Yeah. Okay, good question though. Okay, so the typical process is to form the gate first so that you can implant and form the source and drain regions that are self-aligned. Now, why is it important to form the gate and self-aligned to the source and drain junctions? Yeah, so the problem is, okay, what if you fabricated a transistor that looked like this? It wouldn't work properly, right? Because you form an inversion layer. Okay, so how are you going to get? I mean, you're going to have some really highly resistive, semiconductor region here for current to flow. So basically, if you don't have a self-aligned source drain region to the gate, then it can result in poor transistor performance. Or another way you can deal with that is just draw the gate larger, okay, to guarantee that even if you have misalignment between the gate and the source drain regions, you'll always have, you'll always be able to form an inversion layer all the way from the source to the drain. But if you have this particular case, then you have extra capacitance, and that can slow down your circuit, right? So basically, you want to minimize the gate capacitance needed to form your transistor. So the best way is to perfectly have your source and drain region start kind of where your gate electrode stops. Okay, so that's very important. Now you need to anneal. So this involves thermal annealing to activate. So we call it activate. So we need to heal the crystalline damage and to get the implanted dopant atoms to reside on substitutional lattice sites, right? So they bond with 4 nearest neighbor silicon atoms. And so that requires high temperature processing, usually greater than 600 degrees C, typically up to 100, actually more than 1100 degrees C, depends. The peak temperature can be higher than that. So you need high temperature to heal the damage and to activate the dopants to get the conductivity to be high in the source drain regions. Okay, so what do we do? So now the next step is to form these spacers. Okay, so we form the shallow source drain regions. And the next thing is to form these, what we call gate sidewall spacers. Okay, and then we can do another implant step, except now implant the dopants more deeply to form the deep source drain regions. I guess that's not shown here. Okay. So you form the deep source drain regions after forming the gate sidewall spacers. So the gate sidewall spacers block the deep source drain implants. So this way you can have self-aligned deep source drain regions that are offset from the edge of the gate by a precise amount. So let me explain how we form the sidewall spacers. So let's say this is the gate. What we do is we conformally deposit a dielectric layer. Okay, so there's some processes where you can deposit, uniformly coat a thin film over any topography on the surface of the wafer. Okay, and notice that if the thin film, if the spacer material is deposited, okay, so first of all, well, let's look at it this way. So you form this nice conformal layer. Notice that the vertical thickness here is greater than the vertical thickness here. Right? That's the natural consequences of a conformal deposition process. So now what we can do is we can etch anisotropically. Okay, there's always going to be some corner rounding during the etch process. So basically you can have a directional etch. So some etch process, we call this an anisotropic etch. So anisotropic etch, in other words, it etches faster in the vertical direction than the lateral direction. Okay, so basically you just etch down, remove the thickness, vertically. So you can actually you can clear the dielectric like over the gate and in these source drain regions, but you haven't cleared it from the sidewalls of the gate electrode. So basically this is how spacers are formed. You deposit a thin film conformally and then you etch back anisotropically to form these spacers. And the width of these spacers is actually correlated to the thickness of this deposited layer. Okay? So the spacers actually can be very, very narrow because it's not limited by the lithography process. It's not limited by the light shining through a mask to define these electrodes. So, so the spacers, that's why it's on this slide is showing the spacers are kind of smaller features, narrower features than the gate electrodes, which are defined by the lithography process. Okay? All right, so once you form the gate sidewall spacers, then you can do the deep source drain implants and do further annealing. Okay? Actually, the annealing might be done at the end. A single step can be used to activate dopants both for the source drain extensions as well as the deep source drain implants. Okay? And notice, okay, so this is NMOS on the left, PMOS on the right. You have P plus, source and drain regions, N plus source and drain regions, and PMOS. But you need to form a body contact. So this is going to be P plus body contact for the P well. And on the right side, you have an N well for PMOS. So you need to have an N plus ohmic contact. To form an ohmic contact to the metal, to the N well, you need N plus on the right and P plus on the left. Okay. All right, and then finally, we deposit oxide and cut holes through it wherever you want to form electrical contact to the source and drain regions, and deposit and pattern thin films of metal to form the wiring to interconnect different regions of transistors together to form your circuit. Do you have a question, Haley? Okay, so remember a practical ohmic contact. Okay, so the wells, so these wells are not very heavily doped normally, right? The channel region of a MOSFET is not doped like 10 to the 20 or something like this. So if you want, so usually when you're trying to make a contact between silicon and metal, there's always going to be some Schottky barrier height. Let's say for a contact to N-type material, you have a Schottky barrier height for electrons. So basically, to get current to flow into or out of the silicon, you have to make that tunneling barrier really narrow. So you have to locally dope the silicon very heavily. So basically, in order for the metal to have an ohmic contact to the wells, you have to dope it very heavily at the contact, only at the contact. Okay? Okay, let's look at some cross-sectional transmission electron micrographs of CMOS devices that have, in recent generations of technology. So, pretty much Intel publishes their work at this International Electron Devices meeting in the same year that their product is introduced. Okay, so you can see every 2 years, right? It's like clockwork. Every 2 years, they reveal the details of their latest CMOS technology that's used in products. And so you can see 10 years ago, the industry was at the 90 nanometer node. So this meant that the minimum half pitch, so this is the minimum half pitch. So pitch is kind of like line-to-line spacing, and so half of that. That's kind of the number that people use to label each generation of technology. So 10 years ago, they're at 90 nanometer. Today, we're actually at 22 nanometer, and next year, they're going to introduce 14 nanometer technology. Okay, so looking at these devices, let's label this. So this is wrong color. The gate length, LG. You really can't see the junctions so well here, but these are the sidewall spacers here. Okay, so what they have is they have what we call a dual sidewall spacer. So there's actually a layer of silicon dioxide here and silicon nitride as a spacer. But anyway, so these are the dielectrics that offset the deep source drain region from the more lightly doped shallow source drain extension regions. Okay, and the top of the gate is silicided. The polysilicon gate is silicided, just like the source and drain regions here in contact areas. They're silicided. Okay, so silicide is here and there. So basically, the deposited metal heated up, it reacts with the silicon. So since the gate is silicon and the source drain regions are silicon, then they form silicides there to reduce series resistance. Okay, at the 65 nanometer node, and so these are like the tungsten plugs, right? The metal, the holes that are filled with metal to make electrical contact to the source and drain regions on either side. So here's the gate length. And I guess it's a composite spacer again, but this is the length of their gate sidewall spacers. Okay? And, okay, sorry, if it's not obvious, the silicon is down here. Okay. All right, so one thing to notice is that as Intel advanced its technology, the gate length actually didn't scale down too much. It's about 45 nanometers at the 90 nanometer node. It's about 35 nanometers at the 65 nanometer node. And then at the 45 nanometer node, it stayed at about 35. Okay, so basically, gate length, key thing is that the gate length has not scaled. Even though we're packing more and more transistors to get in closer together, so that means the source and drain regions are getting shorter and shorter, right? So now you can see like here's the gate electrode for an adjacent transistor. Now you're seeing that, we're packing the transistors closer and closer together, but the actual heart of the transistor is not being scaled down. Okay. So we'll explain, well, the reason for that is because it's been too difficult to suppress off-state leakage and to get good on-state current. Because you need to dope the channel more and more heavily if you, bring the scale of channel length down. So fortunately, there was room to just scale the size of the source and drain regions and still pack more transistors in per unit area without scaling down the gate length. But actually, we're running out of room to scale the source drain lengths. And so eventually, the industry does have to start to reduce the gate length again. And that's why they've gone to advanced transistor structures, which we'll cover next time. But in the meantime, we've been able to get higher and higher performance out of each generation of technology. So as I alluded to here, Intel's been able to boost transistor performance. In other words, enhance I-on for a given I-off, even though they're not scaling down the channel length. So this is illustrated, we're showing a close-up now of an NMOS device on the left and PMOS device on the right. So basically what Intel introduced, okay, so starting in the 90 nanometer node, Intel introduced strained silicon technology. Okay, and with each generation of technology beyond that, they've strained the silicon more and more to boost transistor performance. Starting here, they introduced high permittivity metal gate stacks. So basically, starting at the 45 nanometer generation of technology, we had these in addition to strain. Okay, so if you strain a channel, okay, so on the NMOS side, we have tensile strain. Okay, so electrons flowing from the source to the drain. This is just qualitatively, if you pull on it, if you induce tensile strain, that means you're pulling the atoms farther apart. What do you think that does to electron mobility? It increases it because you're decreasing the scattering. I mean, if the electrons can move, if you sort of space the atoms farther apart, then they're vibrating, right? So the chances of electrons drifting through the channel and scattering are reduced. Like the rate of the scattering rate is going to be reduced if you space the atoms farther apart. Okay, but what about holes? How does the mobility of a hole, which moves from one covalent bond to another, how does the mobility of a hole change if you stretch atoms farther apart? Decreases. So in the channel of a PMOS device, they actually introduce compressive strain. So they actually force the atoms to be closer together, so it's easier to move from one covalent bond to another. Okay, so Intel introduced some capping layers in the NMOS device. So those dielectric layers that sort of electrically insulate the NMOS device, they also cover the source drain regions. They actually have strain in those dielectric capping layers, and that induces tensile strain in the channel. Also, you can have strain in the gate material to induce this tensile strain to boost mobility. For PMOS devices, what they did was they etched down, they recessed the silicon, they etched away the silicon in the source drain regions and regrew silicon germanium, germanium has a larger lattice constant, it's a larger atom. So naturally, it actually wants to have the atom spaced farther apart. But basically, the silicon germanium that's grown there is under compressive strain, because you're forcing the silicon germanium to grow matched to the lattice of silicon. So the silicon germanium is actually feeling squeezed, and it wants to expand. So near the surface, it wants to sort of expand, and that induces compressive strain in the channel. So this boosts hole mobility for PMOS. Now the high K dielectric and metal gate, it gets rid of polygate depletion, and it gives you better capacitive coupling between the gate voltage and the channel potential. So you actually can improve the effective oxide capacitance, and that improves your on-state, the inversion charge density, and better gate control for better short channel effects. Okay, so that's what the industry has done up until last year when Intel made a radical change in the transistor structure. But Louis? The question is how much strain? That's a good question. The silicon has a strain limit. It'll crack, if there are any material scientists in here. So it'll crack if you really put too much strain on it, like more than 2% strain. So the amount of strain in here, I don't know, let's see, Peng, do you remember? It's approaching 1%. Approaching 1% in the most advanced technologies today, right? But if you go much beyond that, you'll see cracks. Actually, defects start to form in the silicon. Yes, Haley? Oh, okay. So that's a good question. What are these things? Yeah. Okay. So they grow the silicon germanium. Oh, and then they have raised source strain. Okay. So starting. So in some of the most advanced technologies, rather than so you want to have thicker source drain regions, right, to minimize series resistance. But if you make the source drain junctions too deep and they're too close to the channel, then that induces drain-induced barrier lowering and VT roll-off. Okay, so the short channel effects worsen if you have the deep source drain region close to the channel. So basically, rather than making deeper source drain regions, they actually grew epitaxially silicon on top of the surface, right? So the surface of the source drain regions is actually raised. So they're thicker, but that way you can get away with not too deep of a source drain junction. Right? So series resistance of the source drain regions is mitigated, but you don't have really deep source drain junctions, so you can actually suppress short channel effects. No, so they still have source drain extensions like here, doped source drain extension regions here, and this is the spacer, right? The gate sidewall dielectric spacer. But then they raise the source and drain regions, and make here's like the tungsten, the metal plugs that contact the source and drain regions. Okay? Yeah, good observation. Okay, so CMOS power crisis. I mentioned this last time. If you look historically, this is not updated, but just you get the gist of it. The threshold, the supply voltage VDD has really stalled in terms of scaling, being reduced. It's hard to reduce the threshold, the supply voltage for a CMOS circuit too much below 1 volt, because you can't really lower the threshold voltage to be too close to 0, otherwise the off-state leakage current goes up exponentially. So if the VT cannot come very close to 0, like it has to be 0.3 volts or so, not too much lower than that. If you want to have significant gate overdrive, VDD minus VT, then for reasonable circuit performance, then you can't really scale down the supply voltage. So in the previous decade, people were just charting the trend in CMOS technology advancement. As we scaled down the gate length, we did scale down the threshold voltage, so the leakage current, the power wasted due to leakage current grew exponentially. But because we didn't scale the voltage proportionately to the transistor size, we ended up with also increased active power density. So the power needed to just switch transistors per unit area went up because you're fitting more and more transistors in a given area, but you're not lowering the voltage. So this basically was a concern that people were projecting. Okay, if we continue at this rate, the CMOS chips will get too hot, right? Hotter than a hot plate, like I mentioned before, approaching the level of a nuclear reactor. So that was the reason why in the last decade we went to multi-core processors. So actually, we can purposely slow down the circuit, so we can actually scale the voltage down, but you're going to get a slower circuit operation. But now you have multiple cores. So this plot on the right shows the trade-off. If you have the trade-off in the energy needed to perform a certain digital logic operation. So that's on the right here. So on the vertical curve, we show how much energy does it take to perform a digital logic operation. And on the horizontal curve is really the delay. How much time does it take to perform that operation? Or it's 1 over throughput, okay? So in other words, how many picoseconds does it take, do you have to wait for the operation to be completed? So there's always a fundamental trade-off. If you you can lower VDD, okay, to save. So this means 1/2 CV squared goes down, right? That's the energy needed to charge up a load capacitor, okay? So 1 over CV squared goes down. So the total energy needed to perform your operation goes down. But the speed of your device goes down, right? Because the ID sat or I effective goes down if you scale down the voltage, okay? So there's a trade-off, fundamental trade-off. If you want to save energy or operate more energy efficiently, then you have to operate your circuit at a slower speed. But if you have multiple circuits working in parallel, then you can actually achieve the throughput, right, the system throughput you wanted, but operate more energy efficiently. Okay, so that's fundamentally the reason why the industry, you don't see the the gigahertz clock speeds going up anymore. As you scale the technology, you see the number of cores increasing. Okay, it's basically this power density challenge. So next time we're going to talk about advanced transistor structures. But the key here to lowering the supply voltage is to actually improve gate control. So remember, the subthreshold swing is really proportional to 1. Let's see, this is C total, so C depletion plus C aux over C aux, right? S is proportional to that. So the steeper the subthreshold swing is, in other words, the better gate control you have, then the lower your threshold voltage can be. So you can actually lower your supply voltage and still have high I on and low I off. Right? So the key for advanced transistors is basically to improve the gate control. So if you have better capacitive coupling between the gate and the channel compared to capacitive coupling between the channel and the body, and the capacitive coupling between the drain and the channel. Right? So remember, when the transistor is off, the drain voltage is high. So the drain through this through the depletion region can capacitively affect, couple to the channel potential to lower the source potential barrier. So you can think of that effect as a capacitive coupling effect. So basically, this subthreshold swing actually should also include C, the drain, right? It's a total capacitance. So you want the gate capacitance to be dominant over the total capacitance in order to have the subthreshold swing become steep, and the ideal limit is 60 millivolts per decade. So only if you can come up with a transistor design that has improved gate control compared to the planar bulk device can you actually help to enable the supply voltage to be reduced. Okay? And that's basically, so the first product which has advanced transistor structures that we'll talk about next time is this Intel Ivy Bridge microprocessor. And notice it has multiple cores, and it has over 1 billion transistors, and it doesn't say. Yeah, well, it has 3-dimensional transistors, which we will cover next time. Okay? All right, have a good weekend. I'll see you Tuesday for the quiz.